Hey guys, I'm going to talk to you about implicit versus explicit differentiation. And so far, we've been working with explicit differentiation. And so we were given functions like y equals 3x squared minus 4, or y equals 1 over x, or y equals 2x squared minus 3 over 5x. All right, and so what you notice is your y is solved for. Everything on the right side is only with x's, and so we would take the derivative with respect to x. And so on the left side, right, when we take the derivative with respect to x, we'll do the first two here. We'll get dy dx, and I know we've used really y prime, right? Using the power rule here, we get 6x. Here, when we take the derivative dy dx, we would get negative 1 over x squared. I'm not going to do this one. But sometimes we're going to be given functions that are a little bit more difficult. They're not solved for y, and these are called implicit functions. And so an example could be xy equals 1. We have a circle here, x squared plus y squared equals 9, so that's a circle with radius 3. And in either of these cases, we might want to find the tangent to the curve at any point. And some are easier than others. This one we can solve for y, and we would get y equals 1 over x, and so we would get this same result here. But if you look at x squared plus y squared equals 9, it's a little bit more difficult to solve for y. We would have to do y equals plus square root of 9 minus x squared, and then we would have to do y equals negative square root of 9 minus x squared. And so depending on our point, we would have to use the different derivative here. Implicit differentiation, though, allows us to take the derivative when y isn't solved for, because when we take dy, or when we take a derivative with respect to x, we're going to get this dy dx, and that's what we're always looking for when we want to find the derivative. We want to find dy dx. So let's look at xy equals 1, and we're going to differentiate that implicitly, meaning I'm not going to solve for y. And so if we look here, we have a product, right? We have x times y, and we're going to differentiate both sides with respect to x. And so using our product rule, we have the first times the derivative of the second. So again, x is the first function. I'm taking the derivative of y with respect to x, plus my second function, which is y, taking the derivative of x, right? Really what we're doing is we're saying that's dx dx, and so that's just 1, equals, and then we're going to take the derivative of a constant, which should be an x, and so that's just 0. And so we get dy dx times x equals negative y, and so dy dx equals negative y over x. Now, this doesn't look like what we got up here. Dy dx is negative 1 over x squared. But if we were to take a point on this curve, and so let's say we took the point, we're concerned about the tangent at 2, 1/2, right? So when x is 2, y is 1/2. Well, if I use my explicit differentiation, right, we'll get dy dx equals negative 1/4. What happens here, right? If we know the point 2, 1/2, I'm going to plug in dy dx. I'm going to plug in a 1/2 for my y, so I get negative 1/2 divided by 2, and when we simplify that, we get negative 1/4. So it doesn't matter which one we use, explicit or implicit, we're going to get the same result for the value of the tangent at that point. Now, this one we could have solved for y and just done it explicitly. However, you're going to see more difficult ones like x squared plus y squared equals 9, where you just can't solve for the y as easy. And so we're going to use this implicit differentiation.